Welcome! My name is Rachel, and I'm a member of the product support team at Biognosis. In this tutorial, I would like to introduce you to the input normalization and stoichiometry calculation options available as part of the PTM analysis workflow in Spectronaut. Spectronaut offers a dedicated PTM workflow that provides extensive support for proteomic studies involving post-translational modifications by offering site-based localization, quantification, and regulation analysis. Additionally, Spectronaut features two other advanced PTM-related features: input-based normalization of enriched samples and calculation of PTM site occupancy. In proteomics experiments where modifications are studied using an enrichment step, it is important to decouple the changes in PTM site quantity from the changes in protein abundance in the original sample. This is achieved by performing input normalization of PTM site quantities using pre- and post-enrichment match samples. Additionally, an important aspect of PTMs is the rate of site occupancy, or stoichiometry, which can provide biological information irrespective of the underlying protein abundance. In Spectronaut, accurate and precise PTM stoichiometry calculations are carried out using flyability ratios. Such ratios are calculated at the precursor level using non-modified and input normalized modified precursor quantities from pre- and post-enrichment matched runs. Alternatively, both precursor quantities can be selected from the same sample, enriched or non-enriched, for a given PTM. If you have matched pre- and post-enrichment samples and want to use input normalization, you will perform separate Spectronaut searches for your non-enriched and enriched samples. When searching your non-enriched global proteome files, it is optional but recommended to enable the PTM workflow and include the variable modification of interest. When setting up the search for your enriched files, Spectronaut assumes that you have already searched your non-enriched samples separately and have the SNE file from that search available. Alternatively, for larger experiments, it is possible to analyze the whole proteome and enrich samples independently and link them afterwards, generating a third SNE file for the enriched samples that includes input normalization. Let's move now to Spectronaut and walk through how to properly set up your analysis to take full advantage of these features. Here, I will use phosphorylation as an example, but the same concepts are applicable to other post-translational modifications of interest. Once you have the SNE file with identified peptides from the non-enriched global proteome samples, you are ready to set up a direct DIA analysis for the matching post-enrichment samples, where you enable input normalization and optionally stoichiometry calculation. Let's start by uploading our PTM enriched runs and selecting the appropriate FASTA file. Next, you will adjust the search settings to add your variable modification of interest to the search space generated on the fly. The PTM probing search mode option available here enables fast querying of dozens of potential variable modifications simultaneously, thanks to the Kuiper search engine that works alongside Pulsar. However, this open searching mode should only be used in an initial search to probe which PTMs might be present. For analysis where input normalization and stoichiometry calculations are included, it is recommended to use a closed search with only variable or fixed modifications to ensure the highest sensitivity. Additionally, for phospho-enriched samples, it is recommended to update the quantification settings so only phosphorylated precursors are used for cross-run normalization. Lastly, the PTM localization filter should be enabled. While it is optional to enable this filter for the Pulsar search step, it is necessary to do so for the DIA analysis step, as this setting turns on calculation of localization probabilities for all selected variable modifications and enables PTM quantification in a site-specific manner. Subsequently, in the PTM workflow node, you will find the options for input normalization strategy and stoichiometry calculation strategy. For input normalization, you have the option to include all peptides, non-modified peptides, or non-modifiable peptides from the input sample. Using all peptides is the most comprehensive option and is recommended for modifications with high stoichiometries, such as phosphorylation. Selecting non-modified peptides is generally advised for modifications with low stoichiometries at residues which are common within the proteome. The non-modifiable peptide strategy is useful when the modified residue is not common within the proteome or the expected modification rate is variable between samples. When enabling the stoichiometry calculation, there are two possible strategies for specifying which analysis file counterpart modified and non-modified peptide quantities originate from. One is to use modified PTM site quantities from the current sample and the unmodified site quantity from the corresponding input sample. This option is suitable for protocols with high enrichment efficiency, including phosphoenrichment. The other selection uses both modified and non-modified PTM site quantities from the current sample, not from the input samples. This approach is appropriate for protein-based enrichment workflows. When one of these two stoichiometry calculation strategies is selected, 3 additional quality filters become available to produce accurate and precise results. Specifically, you can specify a max Q value so that only modified and non-modified peptides with Q values below this threshold are considered for the site stoichiometry calculation. The minimum fold change sets a minimum difference in quantity between the lowest and highest non-modified and modified counterparts to calculate flyability ratios for that peptide. The minimum site localization probability specifies the minimum PTM site probability score required to calculate a stoichiometry value. If an input normalization strategy was selected in your search settings, you will see an extra step in the wizard prompting you to link the SNE file for the non-enriched global proteome samples. Here, you can directly link the saved SNE files or use a sample linking file to ensure the pre- and post-enrichment files are properly matched. It might be necessary to export the sample linking file, modify it, and re-import it to ensure proper linking. If you have only non-enriched or conversely only enriched samples but still want to enable the stoichiometry calculation, then there is no sample linking required. You will leave the input normalization strategy set as none and then set the stoichiometry calculation strategy to modified and non-modified from sample. If an input normalization strategy is selected, the differential abundance analysis is performed using input normalized PTM site quantities. The results of this regulation analysis can be found in the post-analysis perspective using both the candidates table and corresponding volcano plot. Additionally, the PTM versus protein fold changes plot helps users identify changes on the PTM site level that are independent of protein group abundance changes. Specifically, this plot shows protein group log2 ratios plotted against log2 ratios of the corresponding PTM sites. Full descriptions of the other PTM analysis visualizations available here can be found in the Spectronaut user manual. Lastly, input normalized quantities and stoichiometry values can be viewed and exported from the dedicated PTM site report available in the report perspective. Specifically, you can find a field for quantity per protein, which is the input normalized quantity of the PTM site if input normalization is selected. Otherwise, the quantity per protein is the PTM site quantity normalized by its protein group quantity. Additionally, the calculated stoichiometry values can be found here. Thank you for joining, and hopefully this tutorial helps to jumpstart your PTM analysis in Spectronaut.